10 is going to bring back the Pythagorean theorem. More specifically, finding Pythagorean triples. We're going to provide you with a pattern or a formula of how to make that work. But before we do that, let's have a little fun with the Pythagorean theorem. If you have forgotten or do not recall the Pythagorean theorem, we'll just take a moment and recall that. And note that as a squared plus b squared equals c squared. And so they give us this open exercise. I would encourage you to pause it and play with it on a piece of paper and see if you can come up with the idea. Otherwise, I'm going to take a moment and I'm going to walk us through it. But it says Sam and Jill are going to explore a city. Both begin their work from the same walk from the same starting point. So I'm going to use this blue little circle right here as a starting point. It says Sam is going to walk 1 block north. So we'll take one of these and we'll drag it. So Sam's going to walk 1 block north. It says he's going to walk 1 block east. So we'll grab another one of these. So he's going to go 1 block to the east. And then he's going to go 3 blocks north. So let's see, let's just grab another one. 2, 3, right? That's not real good, but let's see if we can maybe move this one over a little bit so it looks nicer. And we'll move this one over. Oh, it doesn't look good. There we go. That looks better. And then it says he's going to walk 3 blocks west. So I want to see if we can grab some of these or not. 1, 2, and then 3. So this was Sam's walk. It says Jill is going to walk 4 blocks south. So 1, 2, 3, and then 4. See if we can get another one. There we go. So she's going to walk 4. We'll clean these up a little bit by sliding that over so that looks a little bit nicer. 4 blocks south, 1 block west. Okay. So we'll go 1 block west, 1 block north. Yep. Let's just grab the right one. Yep, 1 block north. And then we're going to go 4 blocks east. Okay, so this does not want to go. There we go. So look, it made a little square. So 1, 2, 3, and then 4. So they want to know if all city blocks are the same length, who is the farthest from the starting point, right? So if what we're really looking to see is how far Jill is from the starting point versus how far Sam is from the starting point. And so what we can do is we can actually end up creating some triangles that define this. So for example, if I made a right triangle up this way, this would be how far Sam went north and this would be how far to the west Sam would be. Likewise, this is how far south Jill ended up going versus how far east Jill ended up going. So we can calculate this, right, by knowing that he went 1, 2, 3, 4 to the north, and then 1, 2 this direction, and so we could find this C value, and then 1, 2, 3 to the south, and then 3 to the east, and so then we could find this C version here. So that's by doing the Pythagorean theorem. So we could say a squared plus b squared equals c squared, or if we take advantage of it, we would say 4 squared plus 2 squared with a square root is going to equal c. So 16 plus 4 square root, so c is going to equal the square root of 20. And if we did the same thing down here, this would be the square root of 3 squared plus 3 squared. So you get the square root of 9 plus 9, and that would be the square root of 18. We don't need to find out the square root of 20 or the square root of 18. We know that the square root of 20 is going to end up being larger than the square root of 18 just by their inherent nature. So therefore we know that Sam is farthest from the starting point. So our answer would be Sam. So what are we going to do today is we're going to first take a moment and look at example number 1. We're not going to prove, so don't worry if you have any concerns about writing a proof. We're not going to do that here. We really just want to take a look at this information here. And you want to jot this down because we're going to use this in the exercises or next example that we're going to do. So don't worry about proving. Where did I get this from? We were going to write a proof that says prove a triangle with side lengths of x squared minus 1, 2x, and x squared plus 1 is a right triangle. We are going to already assume that in case of this virtual lesson. So we're going to look at example number 2, and it says, next decide an easy way to find Pythagorean triples using the expressions from example number 1, which we're not going to look at. We're pulling this. These are the expressions that we pull from example number 1. Look at the multiplication table below for 1 through 9. Notice that some of the square numbers, 1, 4, 9, 81, lie on the diagonal. They're talking about these right here. 1, 4, 9, 16, 25, 36. Those are all perfect squares. What is the value in part A? What is the value of x? What value of x is used to generate the Pythagorean triple 15, 18, 17 by the formula of x squared minus 1, 2x, x squared plus 1. How do the numbers 1, 4, 4, 16, these are the corners, 1, 4, 4, 16, help us generate the 15, 18, and then 17. So that's what we're going to look at. So essentially what happened is we created a square. I'll highlight that square. And so it started right here in the middle, it came across, and we just picked an arbitrary square. With the purpose here that the 1 was this corner. So we didn't pick a square anywhere on the piece. And so they want us to note, how did we generate 15, 18, 17 with this particular idea? And so that's what we're going to look at. And so this all kind of hinges off the idea that all of this is based off of a 4, which I'm going to highlight. Well, I'm just going to circle it right here. And so if we do this, right, we look at the idea of x squared minus 1. So if we said x squared minus 1, if we said 4 squared minus 1, that would be 16 minus 1, and we get 15. If we did 2x, right, that would be 2 times 4, and we would get 8. And then if we did x squared plus 1, that would end up being 4 squared plus 1. That would be 16 plus 1, and we get 17. So in terms of the square, basically what happens is we take this 16 right here, and we subtracted 1. That would give 15. So we could say 16 minus 1, that would be right here. We could do 16 plus 1, and that would get that. And if we added 4 plus 4, we would get 8. So we're just looking at this pattern. We can generate these all day long in terms of how it works out. So in the next exercise, they're going to ask you to try to create one on your own. Now they're going to give you some very basic guidelines. That way you can think about what it is that was occurring. And so it says to try one. It says form a square on the multiplication table below such that the top corner is a 1. So, right, you want to make sure when you draw your table, you start in this direction right here, and you're going to build a square. So remember, last time the square went out to 16. I would encourage you to pick something, you know, a little bit larger than 16 this time. Maybe 25 or 36 or 49. The choice is up to you. And it says use the sums or differences of the numbers at the vertices of your square to form a Pythagorean triple. Check that the triple you generate actually works. So take a moment and do so. Pause the video when you're done trying one. Unpause the video and see how yours compares to mine. I am going to choose 36. Right, so we'll shrink that. And so if I choose 36, then I know that the corners of my square are 1, 6, 36, and 6. So if I base my pattern on that, I am predicting that I am going to have a Pythagorean triple at 35, 36, and then 37. Is going to be my prediction. Will that be correct? I don't know. Let's find out. And let's see what happens. If we take a note of what occurred, that means I am pulling off of this x value. So if we said x squared minus 1, 2x, and then x squared plus 1. Let's see if we get those three numbers that I predicted. So let's see, 6 squared minus 1, that would be 36 minus 1, and I get 35. Let's see, 2 times 6, that would be a 12. So my initial prediction should not have been 6 times 6, but should have been 6 plus 6. So that would make this a 12. And then let's see, 6 squared plus 1, that would be 36 plus 1, and I get 37. So the Pythagorean triple that we are now working off of is 35, 12, and 37. We want to check and see if that works. So we could do that. We could do the Pythagorean theorem, a squared plus b squared, and see if that equals c squared. So we would have 35 squared plus 12 squared. We want to know, does that equal 37 squared? So this one, right, it might not hurt to grab a calculator. And so if we did 35 squared would be 1,225. 12 squared, we know that one to be 144. I'm going to make this measure. This does not look like a 9. I'll make sure we have a 4. Here we go. And then 37 squared would be 1,369. So if we add 1,225 plus 144, we're going to get 1,369, which is what's equal to this side. So that confirms that 35, 12, 37 is a Pythagorean triple. Right, I would encourage you to try another one. You can do another one on this grid again. A bigger square or a smaller square. You can try it as many times as you want as you're comfortable with the x squared minus 1, 2x, and x squared plus 1. So in this next part for the example, they're going to move us off of the 1. They say, let's generalize this square to any square in the multiplication table where two opposite vertices of the square are square numbers. In other words, what they mean by that is, notice in this piece, this vertex is a 9, this vertex here is a 25, but we're no longer starting here at 1. We're moving the square off of that. How can you use the sums or differences of the numbers of the vertices of the shaded square to get a Pythagorean triple of 16, 30, and 34? So they want us to know, how can we get this using these values? Well, let's take a look. If we did 25 minus 9, right? 25 minus 9, so that would be this vertex and this vertex. That would be equal to 16. If I did, let's say, this vertex and this vertex, right? 15 plus 15. Or you could say 15 times 2. That would give us 30. And if we did 25 plus 9, that would give us 34. So the interesting thing is here is this pattern here is no longer completely governing our piece, right? This one worked because this one is when we focused on having the corner of our square here. Our corner of our square is no longer there. Our corner of the square is now a 9. And so that alters what's going to happen a little bit. And this is where we're going to write our generalized form. See, the x squared minus 1, the 2x, and the x squared plus 1 only works if my square originates in the top left-hand corner. If I move my square off of that corner and go somewhere else, it doesn't do that. So the last part of this, in this example, says using x instead of 5. Now, let's set this up, right? Let's say we underline this for sight purposes. They say instead use x instead of 5 and y instead of 3. Let's focus on where that came from. That comes from, if we look up here at the top, we have this 5 and we have this 3. The values above the box. Now, of course, we can see that same 5 and that same 3 over here. A 5 and a 3. And they say use x instead of 5 and y instead of 3 for your calculations in that piece. So now where is this going? Let's just bring this out. We now have this generalized formula of x squared minus y squared. And then we're going to have 2xy. And then the other piece is going to be plus. Well, not plus, that's comma, x squared plus y squared. This is going to be our general form for creating Pythagorean triples. Right, so if we modeled this and tried it, let's see if we get the triples. What did we say those triples were? We said that was going to be 16. Let's write that down. 16, 30, and 34. Right, so let's see that we make that happen with this generalized form, noting what these are at the top. So if we said 5 squared minus 3 squared, that would be 25 minus 9, and I'd get my 16. Again, note that how that came off of here just by comparison, 25 and 9. I got 25 minus 9. I'm doing 5 squared minus 3 squared. Now if I do 2 times 5 times 3, that would give me 30. That's the same thing as saying 15 plus 15. So we'll circle these just to remind us of that origin. And then the last one, that would be 5 squared plus 3 squared. That would be 25 plus 9. And then we would get that 34. We get that Pythagorean triple. So we started off with x squared minus 1, and then 2x, and then x squared plus 1, and we have now evolved that into the form you're going to want to know for this lesson. And so we'll just put a box around it. This is the takeaway from this lesson, this generalized form. So if you haven't written that down, obviously by now you're going to want to write that down and make use of that. You can also find that probably somewhere in the notes, but I'm not sure, so I would write that down in that design. All right, so that's the end of this lesson. It was a short lesson overall. And now for the problem set.